This one, I just want to, I believe that all of you have already started or either finished the pH lab. So you probably already have a good idea about how a diprotic system works in titration. Basically, you would expect two jumping area due to the equivalence point. At the equivalence point, the pH will change a lot. So you see the sudden drop of pH. Of course, this is the example you're titrating a base with the acid, so the pH will keep decreasing all the way. If you're using a base to titrate an acid, then the pH will increase all the way, right? And we have generally two methods to tell where the equivalence point is. One is by using titrate indicators. So for example, in this lab, sodium carbonate and titrated with HCl, we use phenolphthalein and methane orange to tell the two equivalence point, right? Because their color change is very close to the two equivalence point that you can expect from the system. Now, I have a question for you guys. Suppose that we have 25 milliliter of 0.1 molarity sodium carbonate, and we're titrating it with a 0.1 molarity HCl solution. What are the pH values at the two equivalence points? Okay, we're not considering the activity coefficient here. Okay, just the concentration. So what do you think here? Maybe it's easier to ask another question first. What is the dominating species, you think, at the two equivalence points? So we know that at the beginning we have CO3 2 minus, right? So what do we have here? And what do we have here? That's right. So this one we have HCO3 minus, and this we have H2CO3. Okay. Wait. CO3 2 minus? No, it's not. So at the beginning you start with carbonic ion. And then when you add HCl, the first equivalence one is HCO3, and then the second one is H2CO3. 8.13 and 3.94. Can I ask how did you get this value? Okay, let's say if pKa1 is 6.13 and pKa2 is 9.91. Okay, you can use approximation, right? But based on what theory? What about we think about the second endpoint first? Second equivalence point is H2CO3, right? Combining with what we just mentioned in previous slide, at the equivalence point, it's fully converted to H2CO3. So how do you calculate the pH of the system at this point? pH equals to pKa. Which pKa? So what's the basis of pH equals to pKa? Why? Now, we are actually looking at the diprotic system, right? Can you still remember how do we calculate pH for a diprotic system? We divide them to 3 categories, right? All right. A lot of you say pH equals to pKa2. Do you still remember when does this stand? Because the formula is actually right. So if you want pH equals to pKa2, it means that your HA minus is the same concentration of H2A, right? Do you think that's the case here? Let me ask you this, okay? If I give you a solution, a carbonic acid solution, it's H2CO3, it's a diprotic acid. How do you calculate the pH of that solution? Remember, for polyprotic acid, we divide the species to 3 categories. 1, fully protonated. 2, fully deprotonated. 3, amphiprotic. Right? So what category does this one fall into? Yes, fully protonated. So how do you calculate pH for a fully protonated form? Thank you, check. So what about H2CO3? Check. You cannot use the moles directly unless it's a strong acid. Thank you, check. Yes. When you're dealing with the polyprotic acid and it's fully protonated, you treat it as a monoprotic acid. So the pH will be not the pH. Yeah, I'm actually run here. This is actually pK1. So the concentration of H proton should be Ka1 formal concentration, right? Guys, you really have to review the lecture content. This will be a major part of the exam 3. Does that make sense now? For this part, we're just talking about the second equivalence point. Okay. First of all, to clarify that the equivalence point is when the initial species is fully converted to the second species, right? At the first equivalent point, CO3 2 minus is fully converted to HCO3. And then at the second, HCO3 is fully protonated to form H2CO3. And then you consider it as a diprotic, fully protonated system, right? And to calculate the pH, you treat it as a monoprotic system and use the ICE, the KAF thing. And as Check just indicated beginning, at the before the titration occurs, it's a diprotic system again, but you're dealing with the fully deprotonated one. So you treat it as a monoprotic base using pKb1 or pKa2. Okay. Now, what about the one here, HCO3 minus? Is it a fully deprotonated form, fully protonated form, or amphiprotic form? Amphiprotic. It's amphiprotic, right? So how do you calculate pH of the amphiprotic form? We have that long equation, right? But as I said, you can do approximation, which is pH is half pKa1 plus pKa2. So if you take these two values here, it will be around 8, which is actually why we use phenolphthalein to determine the first equivalence point, right? Now, if you do the calculation here, of course, you need to know the concentration with the volumes. The pH will be around 3 something. Okay, 3 point something. 3 to 4. So, which is why we use methyl orange.